Okay, so that was the pH diagram. We now go to the next type of a diagram, which is again very popularly used, is temperature entropy diagram. On the y-axis is temperature, and on the x-axis is specific entropy. And again, making this plot, you have to have the same caution that we had with the pH plot. Once you have set specific entropy at a particular point to 0, specific entropy also gets set to 0. So specific entropy has the same issues, that specific entropy of nitrogen has got some value, specific entropy of water has some value. The two are not on the same scale. Temperatures are on the same scale, specific volume is on the same scale, but specific enthalpy, specific entropy are not on the same scale. We have to have a common reference point for everything, only then we can compare them. Okay, so now let's look at the TS diagram, and we do the same thing we did for the pH diagram. And what happens here, if you look at any of these substances, what we see is that the saturated liquid states all come on a line like that. This is all the saturated liquid states. Saturated liquid line is called, or x equal to 0. And we continue the same plot. We take all the properties of the dry saturated vapor and make a plot, and it looks something like that. This is all x equal to 1, and we can join all of these. This is the saturated liquid line, and this side we get the saturated vapor line, and at the top is the critical point. So this is the dome again. And what happens here is we can now ask for what constant pressure lines. We can ask for constant enthalpy lines, constant dryness fraction lines, and constant specific volume lines. Okay, so easiest one is x, and this will follow exactly the same style as we had earlier. At any given temperature, x equal to 0 is here, x equal to 1 is here, it is increasing monotonously here. Same with every pressure. So constant dryness fraction lines will all look like that. So these are constant dryness fractions, and they are always inside the dome. Now we ask for constant pressure lines. That's what happens is we do the same, that TV type of a thing here. It starts from here and very quickly, say, comes to a saturated liquid state. Then the pressure is constant, and then from here the constant pressure line begins to go up. Then we come another point there, and then again it starts to go up. At even higher pressures we come there, and finally at the critical pressure we get this critical isobar. So pressures below the critical pressure and temperatures below the critical temperature, we see the phase change taking place. So constant pressure heating from this state will first take this to a saturated liquid state. The specific entropy is increasing. Then it will be followed by constant temperature evaporation, and then it will become a superheated vapor, and then continue on this line. So that's what the constant pressure heating line looks like. Constant pressure cooling line will be exactly the opposite of this, which in our pH diagram was a nice straight line. Here it has become a little more curvy line. Now we ask that this was state 1, this is state 2. From state 2, we undergo an isentropic process. Isentropic process means S is constant, and this will be achievable in an ideal situation in a turbine or a compressor, nozzle or a diffuser. These are all isentropic processes, and these are all slow processes, but that doesn't matter. So what it means is that if S is constant, a turbine or a nozzle attains states which are on this line anywhere. And then depending on if the pressure was there, this will be the state. The pressure was there, this will be the state. Pressure was there, this will be the exit state. And this diagram tells us that if any of these devices were non-ideal, that's what we learned in the laws, then there will be an increase in entropy, which means that while the ideal turbine will have come like this, the real turbine or the real nozzle will go like that to that point. And that will not be a solid line, so this has to be a dotted line. So from here to here, the turbine, ideal turbine will be like this, the real turbine will be like that. The compression process will be exactly opposite. Ideal compression will be isentropic, it will go up. The real compression will, of course, have an increase in entropy, so the line will go that side. So that's how the TS diagram helps us in visualizing all these work-consuming devices. The same is true even at this end, that when you have compressed liquid. So if you are pumping water from this pressure to this pressure, this will be the ideal pumping, this will be the real pumping. And the trouble is, you will see in a minute that all these lines on this side, they are very, very close to one another, and what we draw here as pumping as this state is the ideal one. This is the isobar, and real pumping will be like this. This is a big exaggeration on what we can actually see on the diagram because the lines are very, very close, but in the real world, this is something we will have to take care of. Okay, so that is the lines of constant pressure that we looked at. Now we want lines of constant enthalpy, and what happens is that these lines go like that. So these are constant enthalpy lines. And what it tells you is that if you are going to do throttling from here, that's an isenthalpic process, then the states that one would get will be all along that side and not along this side. Throttling is an irreversible process. Entropy has to increase, so the states will lie to the right and not to the left. You cannot throttle a substance to a higher pressure. It is always to be throttled to a lower pressure. So these are constant enthalpy lines. Specific volume lines are also somewhat similar on this, but of a different slope. And so that tells us everything that we wanted about the TS diagram. And I have illustrated this with a heating process, which is like a cooling process, the turbine and a nozzle, and also the throttling process of this diagram. Okay, now we will see the real TS diagram. Okay, you see a lot of lines over there. This is specific entropy. It is 0 here, which is saturated liquid at triple point. This is the triple point line of water, and this is temperature in Kelvin. So this is for water. And the shape of the dome is like what I've qualitatively shown. And inside this dome, you have the same thing. X is equal to 0.1, 0.2, 0.3, constant dryness fraction lines going that way. Then you have P equal to 0.1 megapascal, 0.2, 5, 10, 20, 100 megapascal. These lines are going up there like that. But notice one thing, that this is 20 megapascal, 50 megapascal, 100 megapascal. So suddenly within this small range, we have had a huge increase in pressure. This side we are going lower and lower in pressure, 0.1 megapascal, 0.001 megapascal. So we are going like now 1 kilopascal. So these are very low pressures. And then if you see this part, practically they have not drawn anything over here. And we know that all these states on this side, and this is now, this extreme line on the right, on the left, is 100 megapascal, very, very high pressure. And this is the saturated liquid line. So pumping water from 1 bar to 10 bar won't even show up on this line. It will be a very, very small line somewhere squeezed in between this here. And that's because the dependence of entropy on pressure is very, very weak. And so we cannot see those lines here. And so although on my diagram, on freehand, we can show all these pumping processes, isentropic and asentropic, if we were to use the real diagram, we cannot even show this, visualize these processes over here, but reality they will be there. And these are the constant enthalpy lines, H equal to 3500. You can see that these lines are going like this. And what one sees interestingly is that as this H line comes in, it is somewhat like a constant vertical straight line here. Then it goes through a turn, and then these lines are pretty much horizontal at this end. Look at this spot. And in a minute we will see why these H lines have become horizontal, which means that H is now 3500 at this particular temperature. So if you pick up any pressure, that doesn't matter, specific enthalpy is the same. It is independent of the pressure, and that's what we will see, that this is what ideal gas behavior actually begins to look like. Okay, so this is the thermodynamic properties of water. And again, now let's see what use I can put this to. And I pose a question that in a refrigerator we use 134A or R22, or in the olden days there was ammonia. Why can't I make a refrigeration cycle or an air conditioning system with water as the working substance? We have steam power cycles, all of them use water. There is no exception in that. Why not use the water in a refrigerator? And so let's begin to look at this. What will happen? Firstly, we cannot go below 0 degrees Celsius. It will freeze. So we have got to make a compromise and say, look, I will give a safety margin and say I will not go below, say, 6 degrees or 5 degrees Celsius. And that means that we will be something like, you said this was 280, this part is 273 plus 6 makes it about 290. So somewhere over there is the lowest temperature we can get. And then we want to reject heat to the environment, so we want to heat it to temperatures above 55 degrees Celsius, say, if it's ambient. So it's about 80-85 degrees Celsius. So that makes it 273 plus 85 is about 360 or something like that. So that will be here, say, approximately. So we have to make a cycle which will operate between these points, 360 and this thing. And so it has to have one throttling process. So this will be a condensation process which will happen at the higher temperature. So it will be condensation like this to liquid, then a throttling, which is H constant line comes here, then here, and then goes back over there, and then you compress it. Constant entropy compression. The trouble is that if you look at 360 and you start looking at the numbers that come out, you'll see here that the specific volume is on the order of, it says 100 meter cube per kg. V. So this is very, very big specific volume. This is vapor at low pressure. It occupies a very large volume. So to get the same mass flow rate, we need very, very big pipes, many meters in diameter, before we can even make this thing work. And to get any reasonable amount of cooling effect, this whole system will become very huge, very bulky. And so you'll have to make a compromise and say, look, only if I can make a compromise and use all of this in a very compact way, then I will use water as a refrigerant. But otherwise, water as a refrigerant is in fact not possible for freezing at all. I can only use it at best for air conditioning, and that is the central idea of what is called a vapor absorption chiller or a vapor absorption machine, where water is the working substance. You operate at very, very low pressures throughout the cycle, and you have to keep worrying that air does not leak into it. And that is where the engineering becomes complex. Now, firstly was size. The second thing, all these property diagrams tells us that pressures of water will be very low, much less than the ambient pressure, which means that I can always expect leakages, and leak will be air into the system. And once air leaks into the system, but partial pressure of air goes up, the performance of the system drastically goes down, and we have a big problem. But that is where the engineering challenge lies. This is a very attractive way of doing air conditioning, because the work or the electricity that it consumes is very, very small compared to vapor compression systems, which is what we use in fridge and ACs. But that's the implication of properties of a pure substance on what we can do and what we cannot do, and why it happens. Okay, so that was the other diagram that I had. And there's a question here, so let's see. Okay, Okay, there is a question which says what will be examples where there will be chemical composition is different at different phases. Okay, I'll come back to it a little later. And I'll come back to it tomorrow after we discuss ideal gases. Okay, there's one more diagram that I will put out, and this is historically a very popular diagram, and a lot of the initial engineering in the early 1900s was done with this plot. And of course, that plot was made by hand. There were no computers or anything. So all these property data were taken, and using freehand and using various things, people made nice beautiful curves and made this picture. And that was the mainstay of engineering into the late 70s. That's when slowly computers started coming in. This is called, this diagram has H on one side, S on one side. So this is the HS diagram, and popularly this was known as the Mollier diagram or the Mollier chart. And a whole generation of engineers did design of thermal power systems and other steam-based systems with this diagram. They plotted the points on this, found out what is what, and that's how they went about doing it. Now remember, we're talking of liquid oxygen and all this. This is also the time in the 60s and 50s last century. There were no computers, and the whole design of putting man on moon and launch vehicles was all done by such diagrams. Right? They're quite powerful tools. On this diagram, the saturation dome is like this, but the saturation point is over here. Saturated liquid line is over here. This is the saturated vapor line. These are lines of constant dryness fraction, 0.76, 0.78, 0.86, 0.98. So we get very good discrimination of dryness fraction here. These are lines of constant temperature. These are lines of constant specific volume, and these are lines of constant pressure. So one can draw all the processes, that where the inlet state to a turbine, where the outlet state, then where the reheat taking place, where the condensation, and we can make the complete cycle on this, and then do all the calculations for sizing of the equipment. Nowadays, it's good to know that this is there, and by showing a cycle on this, we get a very first-hand feel of what this cycle is all about, and what are the possibilities where we can improve, what are the things we cannot do on this diagram. That also becomes clear. Okay, now let's go back to our set. Let's start with the TS diagram. And I mentioned that as we go further and further away, the H lines are becoming horizontal. That means constant temperature line and constant specific enthalpy lines are becoming one and the same. So H is now linearly related to T in some sense. You can look at another way, that if you look at this part of this chart, the lines have somewhat become straight and they are somewhat parallel to one another. Okay. So what that tells us is that that was not the case when we were looking at the lines in this region. Here there are all sorts of funny shapes of the lines, nothing seems to be parallel, nothing seems to be straight, and that is the reason why in this whole region you have very strong non-linearities of behavior of the properties. And that's why we needed to make a very complicated surface like the PVT surface that I showed last time. We fit 60, 70 constant equation to that, and then we are able to compute all the properties. But what this thing tells us is that life has become much more easier. You don't need such a complex formulation anymore. Maybe you can do something much simpler over here. Don't worry about this part. So that is what is happening. And the same thing happens on the TV diagram also. So here is what is going on. If you make the TV diagram, this curve was like that, and you had the critical point at the top. As we go far away, all these constant pressure lines that we were looking at, they become nice, straight, and almost like parallel to one another. Similar thing was happening on the TS diagram. So what it tells us is that somewhere there, and we can say that roughly here there is a region, and there's no hard and fast rule that this is like this and this is in that part. That's why I'm drawing this a little bit zigzag. That here somewhere we can start we're looking at the substance as a gas, and in this whole region, we have to think of it as a vapor. And these are the two very distinct regimes. And within this gas, we will now see ideal gas and real gas. But the fact is that in this condition, where there is a vapor-like behavior, we should not even think of PV equal to I. Completely wrong. And that's why all property diagrams end at some point, and they do not give the chart properties beyond that, because then it is presumed that after these range of pressures and temperatures, the substance behaves like an ideal gas. You can start using ideal gas equations of state, and you can forget about this part. And as I mentioned yesterday, we have several applications where you have the application entirely in this region. So we don't even come into this part. And then we have applications which are entirely in this region, maybe sometimes touching this region, but largely in this. So those have to be treated as vapors, and those other cycles have to be treated as gas. And those few examples where you have some behavior here and some behavior over there, we then have to do a mix and match and very carefully see how properties get added up to give us the total change between this state and this state. Okay, so what we will now do is, say, well, we have defined, say, we have got the first idea, what is something going to be like a gas? And now we continue with this discussion and say, when on this diagram can I say that the substance has begun to behave like a gas? And that tells us that basically we are looking at temperatures in this range where T minus T saturation, or the degree of superheat, is large. We have not yet defined what is large, but we say that, look, if we are far away from this, that means you have heated it a lot more than this saturation temperature here, you can start thinking of this as a gas, at least as a first approximation. And if that condition is not there, it cannot be a gas. So now we will do is, first look at what is the criteria that we have to decide in some more quantitative way whether the substance can be considered to be a gas or it can be considered to be a non-gas. The theory for that goes like this. We look at the critical point. And we say that relative to the critical point, where does the state lie? And then we will define a series, a group of states which we can say are good for ideal gas behavior. Okay, so the first thing we do is